think we're good. So this is, again, should be mostly review, but it's good to refresh our memories. The book has a really nice explanation. Well, whatever book you're using, I'm sure, has a nice explanation of kind of the history of the atom and how it was discovered, how the different parts of the atom were. How it was figured out that different parts of the atom were indeed the different parts of the atom. I'm going to skip over a lot of that because it's an interesting story, but we're a little bit more interested here in the results of what was actually found. So let's first talk about just atomic theory in general. We mentioned this a little bit on the first day when we looked at the the difference between theories and laws. But the development of atomic theory, even though now it doesn't really seem really controversial, at the time really was. And there were a few key ideas that led to the development of the idea that atoms are made of, or matter is made of atoms. So first you got the law of conservation of mass. What is that? Yeah, mass can't be created or destroyed. And now we say in a chemical reaction, because there are certain other processes like nuclear reactions where it can be. But this was actually, it seems really obvious now. We write chemical equations and we say you have this stuff and then it converts into there. But for a long time that was not true. What do you think people thought if you burned something, if you did combustion, what do you think people thought happened before conservation of mass? What? It disappeared, yeah. Because that makes sense, right? That's obvious. You burn something, it's not there anymore. So that was kind of just assumed for, thousands of years. You burn something, it's gone. And then once people could start making really careful measurements of that, we were able to figure out, oh no, actually it's still there, it's just converted to a different form. So that's the law of conservation of mass. All right. So then a bit after that, we have what's called the law of definite proportions. And it's worth probably showing this. So this is the late 1700s, right around 1800. And what people are starting to realize is kind of an unusual thing about matter, or not unusual, a thing that keeps happening about matter. We don't have any way of knowing yet what matter is made of, but we can detect different elements. So elements have started to be detected, different elements have started to be detected. And some people have started to notice that no matter where you are in the world or what sample you have, if you have the same compounds, the elements are always in the same proportion. So if you take 18 grams of water and you break it down into hydrogen and oxygen, you get 16 grams of oxygen and 2 grams of hydrogen. And if you look at the ratio of that, 16 divided by 2 is 8, so you have like an 8-to-1 ratio of oxygen to hydrogen by mass. And that happened, and all water always did that. No matter how much water you started with, if you broke it down into hydrogen and oxygen, you always got this ratio. Didn't matter if that water was coming from, a sea somewhere in France or in Russia or wherever, that kept happening. Now to us that is obvious because water is water, but at the time it wasn't. It wasn't clear that this was actually the same thing made up of the same parts in exactly the same way. And so the law of definite proportion says that all samples of a given compound, regardless of their source or how they were prepared, have the same proportion of their constituent elements. So they're always going to give you the same ratio of the elements. This is before we know anything about atoms. We just know that the ratios of the elements in these materials are the same. And then that leads to, finally, kind of like the thing that really gives us some evidence of atoms, or only really works with atomic theory. the law of multiple proportions. This one's a little bit trickier to put into words, but I'll just read it and then we'll talk about what it means. When two elements, let's call them A and B, form different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. So that's a lot. That may not make a whole lot of sense, but let's look at an example. So let's take two carbon-based compounds. Carbon dioxide and carbon monoxide. Now, of course, by the names and your experience, you probably know the difference chemically between these two compounds. But let's say we're old-timey chemists, and we don't know. We know we have two different compounds. They're both colorless, odorless gases, but one seems to make people sick, right? In a different way than the other one. So what you find is if you break these compounds down, you'll find that carbon dioxide has 2.67 grams of oxygen per 1 gram of carbon. And carbon monoxide has 1.33 grams of oxygen per 1 gram of carbon. So following the previous rule, the definite proportions rule, we find that if you break these samples down, you're getting a ratio of 2.67 to 1 for carbon dioxide and 1.33 to 1 for carbon monoxide. And from the law of definite proportions, it doesn't matter where those samples come from. If you have those gases, that's the proportion. So here's the thing that they noticed that seemed weird. If you take those ratios and you divide those, you get 2, which means there's always exactly twice as much oxygen in carbon dioxide as in carbon monoxide. And if you spread this idea to other compounds, they found that this always happened. Every time you took a bunch of compounds with the same elements, they were always off by small whole numbers, like 2 or 3 or 4. There was never any weird decimals or anything else there. They were always in these nice even numbers. And when you get nice even numbers, what's the conclusion? The conclusion is that you're counting something. If you're getting nice even numbers, then it must be individual things that you're counting. And so that was really, atomic theory was really developed as an explanation, because theories explain the observations, right? Atomic theory was developed as an explanation of this phenomenon. If we're always getting small whole numbers, it must be that there are some things that are combining, and we can actually count those things. They're like discrete individual things. It's not just like some oxygen. It's individual pieces of oxygen. And eventually those individual pieces were called atoms. So then Dalton's atomic theory, which comes out of that, says each element is composed of tiny indestructible particles called atoms. The atoms have the same mass and other properties that distinguish them from other atoms, from atoms of other elements. They always combine in simple whole number ratios, so you can't cut an atom in half and put half in this compound and half in this compound. They're always whole. And then you can't change from one element, atoms of one element can't change into another element. So you can combine them in different ways and make different compounds, but you can't turn one atom into another atom, which we now know is not quite true, because why? Yeah, in nuclear reactions, you are actually turning, because you're messing with the number of protons, so you are turning the elements into other things. All right. So let's look at the actual structure of the atom, which I'm sure you have heard before. So what's an atom made out of? All right, so we got a nucleus. What's the nucleus? Protons and neutrons. And where is it? In the middle of the atom. So in the middle of the atom, you have a nucleus. And the nucleus contains protons, which are positively charged, and neutrons, which are not charged. They're neutral. We get a couple things from that. So first we get the definition of the element. The number of protons defines the element, and therefore it is also called the atomic number. On the periodic table, on this one here, we see those as blue numbers in the upper right-hand corner of each element. That's the atomic number, and that defines what type of element we have. The other thing we get from the nucleus is the mass. We're going to be really careful with our terms here, because there are a lot of confusing ways of describing atomic mass that we're going to get into in this chapter. But the first one we're going to look at is just called a mass number. And the mass number is the number of protons added with the number of neutrons. That also allows us to define one more term, isotopes. Have the same atomic number but different mass numbers. So when we write isotopes, there's a couple different ways to write different isotopes. First, notice that it's a relationship. So if we write them like this, we're talking about carbon atoms that have different mass numbers. So we're talking about carbon 12 versus carbon 13. Those are different isotopes. One misconception is that there is kind of like a standard, and then the isotopes are the ones that are different from the standard. That's not quite right. All of the different members of all of the different atoms that have the same atomic number but different mass numbers are called isotopes of each other. So carbon 12 is the most common form of carbon. That is still considered an isotope of carbon, as is carbon 13, as is carbon 14. Another way that you'll see them written sometimes is like this. So the word with a dash and then the number. That's how we say it, even if it's written in the previous form. So we say carbon 12 or carbon 13. It also is easier to type that way because you don't have to mess with this superscript. So those are different isotopes, different mass numbers. Okay. So if you want to calculate the number of neutrons in an element, you need to be told the mass number, because those numbers in red on the periodic table are not mass numbers. We'll get to that in a second, but let's talk about electrons first. What are electrons? Yeah. They're negatively charged particles outside the nucleus. They're actually quite far away from the nucleus, relatively speaking. You may have seen kind of the popular descriptions of, or the popular depictions of atoms. We've got a nucleus, and then you've got electrons kind of like spinning around. That's not quite right. We're going to kind of talk a lot about why that's not quite right and what the real structure, what the real electronic structure looks like post quantum mechanics. But it's true that the electrons are outside the nucleus. After we get through this chapter, we're not really going to mention protons and neutrons much anymore. Electrons are really where the chemistry happens. Other than nuclear reactions, which we're not going to do this semester, you'll look at those next semester. Other than nuclear reactions, there's really not anything happening to the nucleus of an atom. When we talk about chemical reactions, we talk about atoms combining, breaking, forming new things, all of that. That all has to do with the electrons. So we're really going to focus on the behavior of the electrons after this chapter. Ions we can then define as charged atoms. And how could an atom become charged rather than neutral? What's happening with its particles that might make it be charged? So it could lose or gain electrons, yes, and then that would give it a state of being charged because it would have a different number of protons and electrons. So any ion is going to have the situation where the number of protons is not the same as the number of electrons. So if we look, for instance, at calcium as an atom, calcium we can look up on the periodic table, number 20. So that's telling us it has 20 protons. If it's a neutral atom, then we would say it also has 20 electrons. How many neutrons does calcium atom have? Sorry, it's a trick question. You can't know just by the identity of the element, because I haven't told you which isotope I'm talking about. If I said how many neutrons does calcium 40 have, then you could say, oh, well, calcium 40 has a mass number of 40. 40 minus 20 is 20, so it must have 20 neutrons. But if I don't specify what isotope I'm talking about, you have no way of knowing the number of neutrons. So since I didn't specify it, we're not going to put it on there. But let's look at an ion of calcium. Calcium 2 plus, or plus 2. You can write those either way. If I have a plus 2 charge on my calcium atom now, I have an ion. How does that change the count of the particles?
The number of protons is the same.
Mm-hmm.
The number of electrons change.
Yeah, so we've got to change the ratio of protons to electrons so that we have 2 more protons, because those are positive. But we can't add 2 protons, because what would that do? Change the identity of it. Yeah, if you have 22 protons, you now have titanium instead of calcium. So we keep our number of protons, and we change the number of electrons down to 18, and then we have a charged particle. Then we have an ion. Positive ions are called cations. And anions are negative. All right. So let's try this. Maybe if I can find an example here. I'm going to make a little table, and then I'm going to ask you to fill in the table. So for each of these, I'm going to give you some information. And you fill in the rest. So for the first one, I'm just going to give you the symbol. And from that, you should be able to fill in the rest. Oh, you know what? I should have one more column here. Let's do mass number 2. All right. So for the first column, you should be able to fill in the rest based on that symbol. The second column, I don't give you a symbol, just some quantities. See if you can fill those in. And then the third line, I give you another symbol. See if you can fill those in. Take a minute to do that. All right, if you think you got those numbers, if you feel comfortable doing so, take a look at the people around you, compare your numbers. If you see differences, talk about where those differences might, or what might have caused those, and try to come to an agreement. All right, so should look like something like this. The atomic number we get from the periodic table, so we look up potassium and we get 19 there. That tells us we've got 19 protons. To get the mass number, in this case it's given, that's just 40. So then we know that the neutrons have to be the difference between the mass number and the number of protons. So in that case that's 21. And then the symbol is written as neutral, not an ion. So that tells us we have to have the same number of electrons as protons. Okay. One of the common mistakes I see here is looking at the periodic table to get the mass number and writing 39 because it's about, that red number is about 39. That's not correct because we're not talking about potassium 39, we're talking about potassium 40. So make sure when you're doing these that you're just looking at the data provided to get those answers. For the second row, we've got an atomic number of 35, which tells us we've got 35 protons. Our mass number is going to be the sum of the neutrons and electrons. 46 and 35 is 81. And then we've got one more electron than protons. So that tells us that our symbol should be bromine 81, and it should be negative. And then for the last line, we've got a positive copper ion, a +1 copper ion. We can look up the atomic number and see that it's 29, telling us we've got 29 protons. The mass number is 63, so 63 minus 29 is, 34? So 34 neutrons. And then to get the number of electrons, we look at the number of protons, recognize that we need one fewer electron than protons because we want an overall positive charge. So that gives us 28 electrons for this one. All right, seem okay? Okay, so we'll stop there for today. A couple reminders. First of all, lab tomorrow. Make sure you're dressed appropriately. Shorts down to the knee, shorts or skirts down to the knee, closed-toed shoes, no sandals or shoes like with a lot of holes in them. And we'll have goggles for you here, of course. Make sure that you have printed out and read the instructions for tomorrow's lab and that you have prepared your notebook for the lab, meaning that you've set it up. There's no particularly hazardous substances. At the beginning of lab tomorrow, we're going to go through some pre-lab preparation type exercises, so don't worry, like do something in your notebook, but don't worry if it's exactly right or not. We'll talk about that tomorrow. In terms of homework and practice, you can get started on Chapter 2 homework. A lot of the problems for Chapter 2 are based more on the second half of the chapter, which we didn't get to today. So it's good if you get started with those now so that you can come in and ask questions on Thursday. Remember, on Thursday we have that extra discussion period for both group work of problems, but it's also a place where you can ask questions from the homework that you're not clear on. Then we'll have another quiz next Tuesday, so a week from today we'll have our second quiz on Chapter 2. Are there any questions or anything else? Yeah.
Preparing for that, where is the instructions?
Oh, so the question is, for preparing for lab, where are the instructions? You'll find them on Blackboard. So you want to look at the schedule, at the course schedule, which tells you which lab we're doing each week, and then find those instructions in the lab section on Blackboard. I will tell you for tomorrow, it's I believe it's are the volumes of pure substances additive. So you will print out that instruction. Please actually print those instructions out rather than just looking at them on your phone. I don't like the idea of people having their phones out on the benchtop in the lab because I've seen them get ruined, and I don't want you to mess up your phone. So if you just print it out, if you don't have a printer at home, you can print here on campus. Your registration includes 500 pages of printing or something like that, so you should be able to print them out here. All right, all good? Great. See you tomorrow morning. Hey.
You said that there was some kind of lab quiz that I need to look up that involved items in this room.
Oh yeah.